This is part 3 of chapter 2, picking up from slide number 24. So in part 2, we fit a quadratic trend model using linear regression to the climate data. Now let's look at the residuals to assess how appropriate this model is in this context. Now, if we, the simple starting point is to look at the sample autocorrelation function calculated by ACF for the residuals. This is resid lm underscore fit. This here is the data minus the fitted values. For this model. Okay, so what do we see? We see some relatively large, significant values at low lags. Now, these are significant relative to the hypothesis test implied by the blue horizontal line that we're going to dig into a little bit more. Okay, so how are we going to understand more what this R plot is telling us? Well, the bottom line is we need to know what R has produced for us. We want to think that the horizontal dashed lines of the graph of the sample autocorrelation function give a measure of chance variation under the null hypothesis that residuals are independent identically distributed. And we're kind of trusting that R has produced something that at each lag H has a chance that the estimated ACF falls within this band is approximately 95% under a null hypothesis of white noise. So under this null hypothesis, only 1 in 20 of the lags of the sample ACF will fall outside this band. So we can see that this null hypothesis doesn't fit these data, right? There's lags 1 and some other similar small lags outside this band. The sample ACF of the residuals is not consistent with a model having independent error terms. Now, we may want to know exactly what this horizontal line is. Where does it come from? How does R construct it? And well, that's going to be homework for the course. Here I'm giving you some hints for how to go about this question. How would you check what R actually does? What approximation is being made? When is this approximation appropriate? Well, this touches on theory. Presumably what R does is drawn on some theoretical results, but it's also a more sort of a practical coding issue to figure out what R has done. So if you type ACF in R, just like any other function, you get the source code for that function. And you see quite quickly that the plotting is done by a service function plot.acf. The service function is part of a package. It's not immediately accessible to you, but you can find the source code of the package you've loaded. And so you have to find out what package it's in, and either from the help documentation or the last line of the source code, you can see that the function is in the package stats. And then once you know that, you have to access that package namespace to find the source code. And the way you do that in R is by this triple colon. So if you do stats : plot.acf, you'll find the source code for that plot, and then you can find what R is actually doing. So if you go through that source code, the critical line is, I think this line I've copied out for you here. It's basically comparing the value of the estimated correlation with a with 1 over square root n, and then it's making a normal test, and this is in fact the standard normal approximation test for lack of correlation that you've probably seen in introductory statistics courses. Okay, so now we know there is correlation. We're going to start thinking what we're going to do about it. And if we knew the covariance matrix gamma for the model with dependent errors, there's something we could do. We would replace the IID model L1 with a model L2, y equals z beta plus zeta, where zeta is normal 0 gamma, and gamma is the covariance matrix. The problem is that even if we know the covariance matrix is not diagonal, it's not these things are not independent, that doesn't tell us necessarily what they are. But anyway, let's suppose for the moment we did know them. Then the minimum variance unbiased estimator of beta is the generalized least square estimator. And I'm not going to derive it for you. I'm going to quote it for you with a reference of Faraway 2002, chapter 5, if you want to check that up. This is freely available as a PDF online. And so here's beta hat GLS estimator. And under this model L2, the OLS estimator is still unbiased. And you can check that as an exercise if you want. And in that sense, it remains a reasonable estimator. And it's very commonly used, in fact. You estimate a trend by least squares, even when you know there's autocorrelation. So the IID error model is not appropriate. It's often a practical solution to use the OLS estimator, especially for preliminary data analysis, because it solves this chicken and egg problem. If you want to estimate gamma, you probably need an estimate of the trend to then estimate variation around the trend. So we use this OLS estimator. It's still unbiased. However, in equation 13, we see a catch. The variance of the OLS estimator has this form, which we're not going to derive, but you can look it up in Faraway or elsewhere. That the key thing is it's different from the variance under model L1. So we have a slightly interesting conclusion. It's okay to do ordinary linear regression for data which are not well modeled with uncorrelated errors. If you do so, you should not trust the error estimates coming from L1. Now, this is an example that needs careful thought about how to use software. And this is something that comes up in other contexts in time series analysis, because we often have to deal with model misspecification. Some parts of the output from the statistical software are reasonable. Here, the parameter estimates from LM. Other parts are unreasonable, the standard errors and any tests based on them. And so these kind of theoretical results, which we've thought about and looked up, help us decide which bits of computer output to use and which to ignore. So I wonder if you've seen situations before where you fit a model using a computer and you then decide some bits are good and other bits are junk. I think often you're in the situation of thinking either it's all good or all junk, but sometimes the truth is halfway in between. And that is the end of chapter 2.